Hello, this lecture will cover pages 216 through 220 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Synchronous Logic Design, Part B, Design Number 3, and Introduction to State Machines. We're going to start on page 216, and before we start the state machine introduction, I want to talk about design number 3 here real quick. Here's your specification as an example for another design. Use the design procedure we discussed on page 210 of the lecture notes to design a JK flip-flop from an SR flip-flop. In other words, all you have is an SR flip-flop and you want to design a JK from it. Well, here's your present state to next state table. I want you to notice something up here, that we're listing a present state because you only have one flip-flop here. It's an SR flip-flop, and you want to make a JK out of it. But we only have one state, but we have inputs. We're having inputs now that we're going to introduce. There's a J input and a K input to the JK flip-flop. So notice that our total number of inputs to this device, okay, is going to be 1, 2, 3. And since there's 3 inputs, that's going to lead to 3 variable map. And notice we just list them sequentially. Now, you could put these in any order. You could put the inputs over here and the present state on the right-hand side here. Doesn't make any difference how you do it, but when you lay it out as the most significant bit to the least significant bit, look down here, when you do your K-maps, you have to, this was usually, remember, your A, your B, and your C, and we had this listed A, B, and C for K-maps, so you have to be careful. However you put this up here, your Q sub n goes down here. Now, I called it present state, but it's Q sub n. I just keep, PS was a present state, but since I labeled that Q sub n, I should probably label this Q sub n down here. And then next is your J, and that's J here, 2 columns. And your K was the last one, which is the 2 center columns, and that's the way we laid out the 3 variable maps. So sequentially, to take care of all possibilities, you list 0 through 7. And that's all I did, was I just listed this in this present state to next state table, 0 through 7. That gets all the possibilities for our inputs. And here's our next state here. Well, if you take a look, how do you want the JK flip-flop to work? Well, if you're at 0 and you get a 0, 0, it's a no change. If you're at 0 on the output, you get a 0, 1, that's a clear, it's 0. If you have a 0 and you get a 1, 0, that's a J, it's a 1, that's a set. What if you have a 0 and a 1? Or what if you have a 1 and a 1 and you have a 0? Well, that's a toggle. A 0 and a 0 is a no change, and you can go through each one of these and see, here's our present state, this is our next state based on these inputs. So I form my present state to next state table. Here's my excitation table that we've used this is the excitation table for the SR flip-flop. We're using an SR flip-flop, so this is the only time that we're going to use an excitation table for an SR flip-flop. And again, just go back and look at the truth table for the SR flip-flop so we can get the excitation table. That's our truth table for the SR flip-flop. And if you take a look, if you have a 0 on the output and you want to stay at 0, well, S has to be 0. And it doesn't make any difference what R is. Because if R is a 0, it's a no change. And if R's a 1, and you get a 0, 1, that's a reset. So either way, you're going to stay at 0. Let's do the next one. We'll do one more. What if it's 0 and you go to 1? Well, S has to be 1 and R has to be 0. There's no don't cares here. If you want to basically take the 0 and you want the output to get set, the only way you're going to do that is S has to be a 1 and R has to be a 0. That's the only way you're going to get a set. You don't have a don't care in this situation. Because the reason you don't have a don't care, remember the SR flip-flop had a 1-1, which was a not applicable. You can't have a 1-1 condition in an SR flip-flop. So that's why these 2 rows here don't have don't cares in them. If you're going to reset the flip-flop, it has to go like this. And if you have a 1 and you want it to stay at 1, I don't care what S is, but R has to be 0. If S is a 0, it's a no change, 1 and a 1. If this is a 1, it's a 1, 0, which is a set. Either way, you get a 1 on the output. So there's our excitation table. And then we go to our next state map. And there's our next state map. That just comes from the present state to next state table. We're up here at the present state to next state table. This is state, you can see this is state 0. There's state 1, 2, 3, 4, 5, 6, 7. If you numbered them out here the way I told you, you'd see these subcubes down here. And you just put the 0, 0 in here, 0, 0. And for the first, that's the 0 state. For the first state, you get a 0, 0. There's your 0, 0. For the third state down here, for 2, you get a 0 and you get a 1. There's a 0 and a 1. And down here you get a 0 and a 1, and there's your 0 and a 1 for your fourth subcube. And then your third subcube, and then your fourth, fifth, sixth, and seventh. You form your next state map. And then what you're going to do is going to go to your final output maps. And the good news is you only have one flip-flop. There's your present state, which we called Q sub n. You can make these both Q sub n in your notes, because I'm referring back to here. Makes it a little easier to understand, Q sub n. And then you can see that the S input has to be J and present state bar, or Q sub n bar. And for the R input, on the SR flip-flop, the map tells us in a reduction technique that the reset is simply equal to K and the present state, or K and Q sub n. And you just realize the circuit, and here's the circuit down here. That's how we take an SR flip-flop, and this is how we make a JK out of it. This whole thing is a JK flip-flop. But you know what? You already knew that. If we go back and look at page 173 in the lecture notes, you know that how do you make a JK flip-flop? It's simply the SR latch with steering circuitry. Do you remember that? Let's see here. Yeah, let's take a look at that. Remember this? This is basically this is back on page 173 of your lecture notes. There's your SR flip-flop, and you take the Q bar output and you feed it around with an AND gate to the set input, or the J. It becomes the J input here. You feed it around the Q bar, and it comes around to the J input. And what about the K? Well, the K was simply the Q output fed around, just like the J was simply the Q bar output fed around. And you can see that here. Here's the Q, feeds around to the steering circuitry for the K. And here's the Q bar. You can see it's fed around to the steering circuit for the J. In this diagram, we just brought the terms, we crossed them over out here and brought them around, but this is laid out a little bit differently here. I crossed it on the input. Here they're crossing it on the output. But if you follow it, you can see that we already knew this design, but it's a nice little procedure to go through. That was design number 3. And then finally, on page 218, we're going to talk about sequential logic applications using state machines. Page 218, very important page. You can look in your book and read a little bit about state machines, but state machines refer to a circuit that sequences through a set of predetermined states. These states are controlled by a clock and are a function of inputs that are both combinational and sequential feedback from the current state. Okay. The overall block diagram of a state machine is shown here. Let's take a look at it for a minute. Notice we still have inputs, and we have combinational logic with these inputs. But what we're doing is we're feeding some of the memory circuits, some of the outputs of the flip-flops back to the inputs. And what we're doing is we're adding on to the total number of inputs we need. In other words, we're taking the outputs, which represent the states of the output, helps us with a history of where we're at. And based on where we're at, we feed them around, and with the combination of these inputs, it tells us where we go on to the next state or on the next clock. And then it sets up a history, and then based on that history, when the clock comes, we know where we go the next time we get a clock. And then we produce these outputs. This block diagram of the state machine is very, very important for you to look this over and understand it. We have feedback, and the feedback comes from the outputs of the flip-flops. No, why are we doing this? I mean, what's the whole reason for the state machine? Well, if you take a look in different designs, for instance, a car wash, you design a car wash controller. You have to know where you were at to know what you do the next time we want to go into a different state. Were we previously in the wash cycle and now it's going to be the rinse cycle? Or were we previously in a soak cycle, so the next sequence, in part of the sequence, the next step is going to be a wash cycle? Were we part of the rinse cycle, so the next state we go into is going to be part of a dry cycle? So think about that. How are you going to know digitally whether you were in rinse, whether you were in pre-soak, whether you're in wash, or whether you're in dry? Well, they're just states. They're just states. The design engineer just makes arbitrary binary states to represent every condition or every state you want to establish as a reference point. What about a digital combinational lock controller? You can design a digital sequence controller where digitally you have to push a 7, an 8, and a 1. And that's the only time the lock will open. You have to push a 7, an 8, and a 1. Well, if you push a 7, then if you push an 8 next, you know you're on track, but you had to know you had a 7 previously pushed. And then if you push the 8, then you push the 1, you know you're on track, open the lock. You're only going to know that if you're looking at the previous state, which was represented an 8 condition, and the state before that represented a 7 condition. So you'd have to know where you were at, and in this case, what button you pushed before you pushed the present state button. All type of digital sequences. You could design NASA could give you a digital sequence for a rocket launch. And there's 20 things that need to be set in a particular order before you can launch that rocket. So you define 20 different states with binary numbers. You do your state transition diagrams. What about the deflection shields? You want to put the deflection shields up when the Cleons are coming for the USS Enterprise. Yeah. Well, think about that. You want to go ahead and come up with a state machine and make sure things are in a particular order. When Spock hits that button to put up those deflection shields, it'll react to that and it'll put those shields up, providing certain other things were done sequentially before it. What that would have been, I don't know. You're going to have to ask Captain Kirk. But there's a lot of application for these things. There's 2 different types of state machines you can talk about. There's the Moore model. In this model, which is shown above, there are no additional inputs to control the outputs. And then the Mealy model, in this model, the outputs are also controlled by additional input signals. In other words, if you take a look at our model up here, here's our feedback coming back from our flip-flops, so we know. If you have 2 flip-flops, you have 2 lines coming back. If you have 3 flip-flops, you have 3 lines coming back, because you need to know what state you were in before the next clock comes, and then based on these inputs, you react. But if you're looking at the Mealy model, there's inputs right here. If you're looking at the Mealy model, there's other inputs right here that'll control these output circuits. But we're not going to have any additional inputs that tie into the output combinational logic. We're not going to have these. Therefore, for the next 5 examples, we're doing state machines using the Moore model, which is shown right here. Now, let me tell you one more thing before we move on here. If you take a look here, once you establish your present state to next state table, you'll see this procedural thing as we go. But if you have 3 inputs like I have shown here, A, B, and C, and you have 1 flip-flop, there's 1 line coming back, and that gives you a total of 4 inputs. You're going to use a 4-variable K-map. What if you only have 2 inputs? Forget about C. C's not here. You have A and you have B, as external inputs that are going to control your circuit, and you have one flip-flop here, because you only have to memorize two different states. Well, one line's coming back, and that's going to give you an A, a B, and one feedback. That's 3 total inputs. That's a 3-variable map. What if you have 2 inputs, A and B, and you have 2 flip-flops because you needed, let's say you needed 2 states or 3 states, or I'm sorry, you needed 3 states. If you needed 3 states, you're going to have to go to 2 flip-flops. So there's 2 lines coming back here. So if you have an A and a B, and you have 2 flip-flops, that's 4 possible inputs. You're going to use a 4-variable map. So all you do is count the total number of inputs you have in your present state table, which include these discrete external inputs plus your feedback terms, which is how many flip-flops you got. And now your total number of inputs will tell you what variable K-map you're using. A 3-variable map, or a 4-variable map, or a 5-variable map, or a 6-variable map. And then on page 219, I'm going to give you some state transition diagrams for state machines. This is the way it's done in the real world. There's a couple different alternatives here, but notice I'm showing you a present state here, and I'm showing you a next state. No, there's many of these as you go around your state transition diagram. But what you'll do is you'll show the circle with a present state, you'll show an arrow, and the arrow represents an active clock transition. And then you'll circle the line here, and when you're in this state and you want to move to this state, you're only going to move from the present state to the next state if these input conditions are true. If A equals something, or B, A equals 1, B equals 1, and C equals 0, or something. So right in the middle of this arrow, you're going to have your input conditions that will allow you to move from here to here. You'll see this in a minute. Once you see it, it's no problem. And then once you get into a state, these are your output conditions. These are your desired outputs to be maintained while you're in this state. So while you're in this state, you want Y. Well, don't forget, these represent signatures. But you want motor A to be on, and you want motor B to be off, and you want, this particular output to be high and this particular output to be low. And once these input conditions are met, you get a clock edge, you go down here, and then you have a whole different desired outputs to be maintained while you're in this state. So right next to the state, you can see your desired outputs. Halfway between, you're going to see your desired inputs to move you to here. And down here, you're going to see your desired outputs when you're in this state. And I show you down here the number of the state circle. The number in the state circle represents the state number and is normally, but not always, listed as binary to correspond to the next state of the sequential memory flip-flops. And then finally on page number 220, alternative state transition diagrams you may see being used, and we'll use a couple of these maybe, but here, notice we have the present state to next state, and present state to next state, and present state to next state. And notice it's a little bit different here. What they're showing you here is when the clock transition comes, these are your desired inputs. A or B or C represent your desired inputs to get to the next state. Then they put a slash and they show the outputs listed too. They don't, they'll show the output listed to get that's to be maintained when you get to the next state. Okay, so basically what I'm showing you in this representation here is with a single input A and a single output Y. So here's this is maintained, but it shows you when you go from this point to this point, A has to be this, and then when you process the circuit through to the next state, Y, the output's this. What if you have 2 inputs A and B and a single output Y? Well, sometimes they'll show it to you this way, where you have A and B, and they'll show A and B here. A is a 0, B is a... If A is a 0 and B is a 1, and the clock comes, you move from state 0 to state 1. And then Y could be a 1. I'm just making something up. And then you're in state 1, you can go to state 2 if this is true, but what if you have 2 inputs, A and B, but there's 4 possibilities for A and B? This is just 0, 1 will get you to state 2. Well, what about if it's 1, 1 or 0, 1 or 1, 0. Well, if you're in state 1, you get in the other 3, you move to state 3. You move from state 1 to state 3. You're not always going to go around clockwise or counterclockwise. You may jump to different states based on the different conditions. And you'll see this as we go through our examples. The next lecture, I think we're going to move on to design number 4. But that concludes this lecture.